Hello, in this session, I will talk about the indefinite integrals. In general, we know that integration is also called anti-differentiation. That's we basically undoing the differentiation process, anti-differentiation. And we also learn how important and how useful it is to know how to solve this type of problem, because solving some certain scientific problems, it will be really helpful. That means, for instance, let's look at that list. Yes. If we know the rate of change, would be really nice to recover the original function. That means, for instance, if we know the velocity of a particle, would be nice to get the position at the given time, or like that this is like displacement or total distance traveled. If the engineering people, if they know the rate of change, for instance, of the water leaking from a tank, they also want to know the amount of the water. If we know the rate of change of how the bacteria population is increasing or decreasing, we would like to know the size of the population at some point in the future. If we know some marginal revenue, marginal cost, then we would like to know the total revenue, like what is the amount, like maybe the demand or supply function. As we can see, all of these and much, much more examples of having or maybe observing the rate of change. Yeah? And then the problem is we have to find a function. Yes, we have to find a function whose derivative is known, whose rate of change is known. That's when we know rate of change and we have to recover the original function. And such a process is called anti-differentiation. That's mean, let's look at this. We did talk about the definite integral. Everything is connected, and we will nicely have we will talk about the fundamental theorem of calculus, which connecting everything. That means, let's look at this. Definite integral is the integral from a to b, f of x dx. F of x is called integrand. Dx like doesn't have really the meaning, just indicates the independent variable. Yeah? And we know that this is a number. What we did, we calculated the area under the curve. Or actually, we have to be a little bit more precise. In the definite integral, it's called net area, because this integral could be also negative if the function is below the x-axis, if function has a negative values. Because the definition, yes, the limit of the Riemann sum, hopefully we remember, involves actually the actual value of the function. I can maybe write a definition. Limit as n goes to the infinity, we know what is n, and then summation starting from, let's maybe say this different way, starting from 1, ending with n, but n is infinity, and then f of x sub I times delta x. That means this is a definition. That's what we did. Definition of the definite integral. Okay, and then sample point x sub I is defined as a plus I times delta x, and delta x is defined b minus a over n, and n is infinity. That's we also know how to evaluate a definite integral using a limit definition. Also, because this limit definition talks about the area under the curve by approximating the area as a rectangles. We remember stripes, rectangles, maybe left-hand side, maybe right-hand side. F of x sub I represents the height, and delta x represents the base of each rectangle. Okay, that means, and this is a number. We know that this could be also negative. That actually was my point, because this is the actual value of the function. Could be negative. Okay, but now what we will do, we will basically remove the limits of integration. That means then what's happened? First of all, we call, that's we may learn new thing today, an indefinite integral. That means this is still the same thing. We will, because integration means anti-differentiation. That means we will still anti-differentiate, but we will more focus on like undoing the formulas that we know. Yes, take the function. That's mean indefinite integral is a function, is also a family of the function. We will discuss this in a minute. And that's what we will try to do. In order to evaluate this, we will, because this is the integral, antiderivative. We have to find the antiderivative. Okay, no more talking. We know that both of them, just one more comment, definite integral and indefinite integral, it will be nicely connected by fundamental theorem of calculus. Okay, let's start. So now this is the definition of the antiderivative. A function f is called an antiderivative of a small f on the interval I if f prime, the capital F prime, equals to f of x. I think probably I hope it's obvious. That means what we can say, maybe I can draw this as an example. If f of x, for instance, is equal to sine of x, yeah, we can reverse. And now we will get the rate of change, derivative. That means everybody knows what's the derivative of sine of x. I can call it f of x based on the labels, notations in the table, and the derivative of sine of x is cosine of x. Now, because we can see this is that rate of change, that given, because now we actually working backwards, that's that given function, that given rate of change. And now, if I will ask you, what is the antiderivative for cosine of x? And you will nicely say is the capital F, yes, the capital F of x is called antiderivative because why? Because we can see and why I can call for the cosine of x antiderivative derivative is sine of x. And now you can, like somebody say, why antiderivative for cosine is sine? Because derivative of sine is cosine. It's actually a beautiful circle because derivative of sine is cosine. I'm just, yes, explaining. That means derivative for sine is cosine. Antiderivative for cosine is sine of x. Okay, that means just in like an example. And that's what we will do today. We will, all of the direct formulas, we will call direct antiderivatives, and especially for trigonometric, it's nice and easy. We will try to reverse it. Okay, that means this antiderivative for cosine is basically sine of x. Okay, now let's look at this one. When we have function f of x equals to 1/3 x cubed, what is the derivative? Derivative is x squared. Yes. If I take now another function really similar, 1/3 x cubed plus 1, what is the derivative? And that's when we're looking at the derivatives, the same cycle. Derivatives. 1/3 x cubed plus 1, derivative is also x squared. Yes. And then 1/3 x cubed minus 1, derivative is also x squared because derivative of the constant is basically 0. Now, when we will take general form, yes, 1/3 x cubed plus any constant, yes, the derivative is also x squared. That means now the question is, what is the antiderivative for x squared? Is the first function, the second, the third one, maybe the last one? That means we will use this plus constant c because constant could be it's basically a family of the function. Because if this is the derivative, the antiderivative could be, yes, anything. It's the same. X squared is basically like the slope of the tangent for all of these because the shape of this function is the same. It's just shifted couple of units down or couple of units up, okay? That means we will call that this equation is the most general form of the antiderivative. Yeah, I still wanted to write this. Derivative, antiderivative, okay? That means now, from now on, if we will be asked what is the antiderivative for x squared, we have to say the main function, 1 third x cubed plus the constant. And we call this constant of integration. Let's actually look at this, yeah, really nicely. That means that's the family of this function x cubed, 1/3 x cubed. Yeah? And we can see this, that actually red lines, which I draw, it's supposed to be, yes, touching the curve, represents the rate of change, slope of the tangent. And it's the same, yes, parallel lines has the same slope, the same for each of them. That's we always have to add this constancy. Okay, and this is the theorem. If f is the antiderivative of the function f, we know what this means on the interval I. The most general antiderivative, yeah, will be f of x plus the constancy, arbitrary constant. We can call constant of integration. Okay, and this is the mean value theorem for this, for integration. If two functions have identical derivative on the interval, then they must differ by a constant. Yes, if two functions has identical derivative. Okay. Okay, now let's look at example number 1, because you will help me to find the formula. Let's start. Let's mean now, what's the derivative of x? Derivative of x is just 1. Derivative of x squared plus over 2 is x. Derivative of x cubed over 3 is x squared. Derivative of x squared over 4 is x cubed. So now looking at this, because that again, that's the derivatives. Derivatives. On the right-hand side, we have derivatives. Now, we probably realize the pattern. If this was x to the power of, maybe let's say this, x to the power of 2, yes, over 2, then we did get 1. That means we basically, or maybe actually, no. Let's look the other way. And this one I can call x to the power of 0, if that's okay. Okay, when we have now, if I will ask you, no, we can still get the derivative of this, correct? X to the power of n plus 1 over n plus 1. The derivative is basically x to the power of n. Okay, now we can look at the pattern. Let's look at the backwards. What is the antiderivative? That means this, talking this way from the right to the left. Derivative, antiderivative. That means antiderivative for x to the power of 1 is x to the power of 2 over 2. Antiderivative for x to the power of 2 is x to the power of 3 over 3. That means whenever we have an exponent, 1, 2, 3, power, in order to create the antiderivative, we can see the pattern. We adding one number. Yes, the exponent is increased by 1 and is divided by the same number. Yeah. Okay, and now having x to the power of n, we will have x to the power of n plus 1 over n plus 1. That means this is the first important formula. We can even say it's a power rule for integration. Okay. One more thing. I have it. One important information. We may use this only for all of the n's, but not for -1, because you can see -1 plus 1 will give us 0. We're not really allowed to divide by 0. This is again, okay, antiderivatives. That's what I can do. I can use the integral notation, since we know, and I will use this indefinite, when we have function x to the power of n dx, and we would like to anti-differentiate, because we remember integration is anti-differentiation. That means antiderivative for x to the power of n is x to the power of n plus 1 over n plus 1. And we will add a constant c. That means this is the first formula. Now, what is happening if n actually is -1? We probably know I can rewrite like this because x to the -1 is 1 over x. And now the question is, what is a function, that question mark, that derivative of this function is 1 over x? Yes, of course. If you're watching this, you probably said this in aloud, natural log of x. We have to put absolute value because natural log is defined only for positive numbers, and the hyperbola 1 over x is defined for all of them, and plus the constant c. That means this is that missing component. Please remember, do not apply that power rule if n is negative. It's basically natural log of x. Okay, that's we know the most general antiderivative for the power function x to the power of n. We adding 1 and we dividing by the same number. Yes. Okay, that's the first one. Now let's try to reverse the trigonometric. What is the, we know the derivatives. I don't even have to ask. For the sine of x plus the constant, oh, yeah, was I thinking about the cosine of x? For the cosine of x is, oh, this is, we're still doing the derivatives. Okay, for the derivative of tangent of x plus the constant is secant square of x. For cotangent of x, negative cosecant square of x. Secant, derivative is secant x tangent x. Cosecant, negative cosecant cotangent. And then, oh, I didn't write. Inverse sine has a derivative 1 over quantity 1 minus x squared. Yes, and inverse tangent, arctangent, 1 over quantity 1 plus x squared. I mean square root of 1 minus x squared. Okay, that's we know the derivatives. And now let's actually write, I can write for all of them, the antiderivatives. What will be the antiderivative, how can I say, for cosine of x? Yes, what's the antiderivative for sine of x? Because we have to be careful with the signs. What's the antiderivative for secant square of x? What's the antiderivative of cosecant square of x? What's the antiderivative for secant x tangent x? Okay, what's the derivative of cosecant x cotangent x dx? And the other one we will write on the other side, on the other slide. Okay, that means we remember this is differentiation process. Differentiation backwards is anti-differentiation process. That means derivative of sine of x is cosine of x. Antiderivative for cosine is just sine of x plus the constant. Now we have to be careful with the sign. Integral, antiderivative for sine of x will be negative cosine of x, because derivative of negative cosine of x plus the constant is sine of x. Yeah, anti-differentiation. Okay, and then secant square, antiderivative for secant square of x is tangent of x, because derivative of tangent is secant square plus the constant. Cosecant square of x is negative cotangent. Yes, we have to incorporate this because derivative of negative cotangent of x is secant square of x. Okay, now integral, the antiderivative for secant tangent is secant of x plus the constant, because derivative of secant is this, and negative cosecant of x. Okay, that means that's the reverse. That's what we working today, the direct antiderivatives, because we may figure out. Okay, and I also have e to the x. Derivative of e to the x is e to the x. Derivative of e to the ax, let's look at this one because this one will be interesting, is e to the ax times a, times the derivative of the inner function. And since it's just the constant, we can figure out. That means now, antiderivative for e to the x, so easy, just e to the x. Now, antiderivative for ax. Yes, that's what we can see. We like e to the ax, e to the ax. Like we did with this negative, we have to divide. That means 1 over a e to the ax plus the constant, of course. Because now we can see when we will find the derivative of 1 over a e to the ax, we have to get that function, that integrand, because we just anti-differentiating. That means I can copy constant and derivative of e to the ax is e to the ax times a. And that's the reason that we need that 1 over a to be cancelled out. Okay, beautiful. And now this one is 1 over x. Then the integral of 1 over x, or antiderivative of 1 over x dx, is natural log of x. We know that we have to put the absolute value because we want to involve all of the x's, of course, except 0. Yes, but from the domain. Then we can accept positive and negative like this. Okay, that's another formulas to remember. And this is just like a table. I didn't put them in the integral notation, but I can do it. Like when we have a function integral, we have to find antiderivative, and that's the antiderivative. Again, when we have addition, yes, this will be the antiderivative. Oh, this one. Let's put dx, we remember, and I can add the constant c. Yes, constant c, constant of integration. Okay, integral of 1 over x, natural log of x, integral of e to the x dx, integral of cosine of x, sine of x, integral of sine of x, negative cosine, secant square, secant tangent. Now, because I didn't write this one, integral of 1 over square root of 1 minus x squared dx is inverse sine and respectively inverse tangent. Okay, that's we have couple of formulas, the same. We can see just the main trigonometric, logarithmic and exponential, and also power form. Okay, now let's look at this one more time. Yeah, that means just what we were doing. Yes, the integral of f of x dx is the indefinite integral of f of x dx is just the process of anti-differentiation, integration. We have to find the antiderivative. F of x plus the constant c is a most general antiderivative. And why this will be true? Because derivative of f of x plus c is back to the integrand f of x. Okay, that means this is called integrand. Yeah, we remember this from the previous section. Integrand, function that we integrating. That means derivative of this must be, and the symbol dx is just, we will call differential, but it's representing an independent variable x, and c is a constant of integration. Okay, I think we know everything. Let's look at this one more time. Power form. Please do not use when n is -1. And why this is antiderivative? Because derivative of this is getting back to the integrand. Derivative of this is basically undoing. And for n equals to -1, natural log of x, absolute value of x. Okay. Also, I have one comment for this one. Oh, actually, I have the other, different function. 1 over x squared dx. That means, first of all, what is the antiderivative? I think I typed this maybe too fast. Let me say one more thing. I can actually integrate here. We may rewrite this as a x to the -2. -2 is not -1. We will use the power rule for integration. That means as soon as we integrating, the integral symbol and dx is gone. Yes, that means antiderivative for x to the negative 2 will be x to the negative 2 plus 1 over negative 2 plus 1. Yes, x to the power of n plus 1 over n plus 1 plus the constant. And then this is x to the negative 1 over negative 1. And we may say that this is equivalent expression without a negative exponent. Okay, that means that's this. And now, yes, I have, this will be always true, yes, always true for all of the x's, but except 0. Because this function is not defined at 0. That's, we can definitely say, because when we have limits of integration, then we know when we can find the area, when we can find the area under the curve. We know when the function is integrable. But for this one, it's still fine. We can do it, but we have to remember that this is true. It will be different, of course, constant for negative x's, for positive x's, but not at 0. And that's always we have to look at this. If 0 is involved, then we will look at something different, improper integrals, but this will be in calculus too. Okay, but now we have to respect the domain. Okay, and one more time, I have the formulas of all of the antiderivatives. That means on the right-hand side now, we have antiderivatives of all of this integrand. Okay, and then this one, because we're missing general logarithmic function, as we okay to flip this and this. That means we know the integral of e to the x, we know the integral of 1 over x dx, but please note the general exponential function. A to the x, the derivative involves the constant. Then we have to divide by this constant for the antiderivative, okay? And maybe this one is maybe too early. It will be later, okay? And then I flipped. We don't really have to look at the cosine at the moment, inverse cosine, okay? That means this one is, yeah, this one is important. And actually, this one, yes, this one is, because we remember the derivative, that means it's just something, if we have to integrate, I can maybe write this, then we can say the integral is log base a of x, but we can also say natural log of x times 1 over ln of a, because the constant. Okay. Now we know all of the formulas. Oh, one more time. One more time, because it's important section, important session. We have to know all of these direct antiderivatives. Now, I always like to ask this question: what is the integral of tangent of x dx? Yes, we still don't know, because we have to find a function that the derivative of this function is tangent of x. Yeah. That means please do not mistake with number 9. Yeah, that's different, because derivative of tangent of x is secant square of x. When, yeah. Oh, okay. But we will uncover that question mark. Okay. Now let's look at this one. Find all function g such that derivative is provided. That means if the derivative is provided, we just have to find the antiderivative. Okay, that's when we have a constant, because we copy constant and we just anti-differentiating a function, we just have to be careful with this division, because we still don't know any rules to undo the quotient rule, the product rule. But in this situation, we may rewrite without the division. 2x to the power of 5 over x is 2x to the power of 4. Square root of x over x is x to the power of negative half. I hope this is okay. Oh, let me write maybe here. Square root of x over x is x to the power of 1/2, x to the power of 1. When we have the same base, xx, and division, we subtracting the exponents, x to the negative half, okay? Okay, and now we can anti-differentiate. copy a constant always. Yeah, we remember from that table above. Antiderivative for sine of x is negative cosine of x. Okay, copy constant. Antiderivative for x to the power of 4 is x to the power of 5 over 5. And antiderivative of x to the negative half is negative half plus 1. It will be half divided by half. And we can just rewrite a little bit nicer. We got x, and that's yes. Yeah. I can also rewrite this. Let's know something. Derivative, yes, integral of the is just g of x plus the constant. Yes, that's what we did. We basically integrated, but I didn't use the integral notation, just to have it that form. Right? We may also notice integration and differentiation are the inverse to each other. They cancel out. It's just g of x. Yeah. Okay, now we can also have rate of change provided, but we may also have some initial condition, extra condition provided for us. And then we may, using this extra data, extra given information, we may compute the constant c. That's me. Let's look at this one. Find f of x if the rate of change is given. F prime of x is x root x. And we also know that the value of the function at 1 is 2. Okay, that means first of all, let's integrate or let's anti-differentiate. We see product, and we remember we have to be careful. We do not know any rules in this session. We still didn't learn any rules to undo the product or the quotient rule. That means let's avoid the product having multiply x to the power of 1 and times x to the power of 1/2, we adding the exponent. That means our function is basically x to the power of 3/2. And now what is the antiderivative? Or we can say, yes, is f of x dx, but this is x to the power of 3/2, integral of x to the 3/2, and this will be x to the power of 5/2 because we adding, divide by 5/2 plus the constant. Okay, and we may simplify. I can flip the fraction because dividing by fraction means multiplying by the reciprocal. Okay, that means this is the most general antiderivative. Shall I rewrite this nicely? X to the 5/2 plus the constant. This is the most general antiderivative. Now, how we can find the constant c, because we may find it since the initial conditions are provided, I can simply say that f of 1 equals to 2. Instead of x, we can replace x with 1 and compute the constant c. That means 1 to the power of any number is 1. We will just subtract from both sides 2/5. Okay, that means c is equal to 2 minus 2/5, 8/5, and this will be the final answer. Yeah, this one or this one. Okay, it's really nice. That means if the initial conditions, some conditions are given, initial, I suppose it's supposed to be f of 0, but if the conditions are given, we will be, this will be extra job for us to calculate the constancy. Okay, and then let's look at, I have another one, but now let's actually see. We have to recover a function, but the second derivative is provided. We have to anti-differentiate once. We will reach the first derivative, and then we have to anti-differentiate the second time. This is the first one. That means this is we integrating first time, anti-differentiating. Yes, formulas, x squared, derivative of integral, antiderivative. Antiderivative for x squared is x cubed over 3. Antiderivative for x is x squared over 2. Antiderivative for 4 is 4x, because Derivative of 4x is 4. We're keeping the negatives, positives, and plus the constant. Let's simplify because 12 divided by 3 is 4, 6 divided by 2 is 3. Okay, that's we do have the first derivative. We did the anti-differentiation. Anti-D, let's say, anti-differentiation. Yes, and now let's do it again. Antiderivative for 4x cubed is x to the power of 4. 3x squared is x cubed. 4x squared is 2x squared, because when we differentiating, we will get back. And now, antiderivative for c is cx plus additional constant. Okay, and now we have the constant c and d. This is the most general form, but we have the initial condition. Let's replace x with 0, and this is equal to 4. Let's replace x with 1, and this is equals to 1. That's we may create a system of two equations. Yes, when we substitute 0, 0, 0, 0, then d equals to 4. That's the first one. And then when we substitute 1, 1 plus 1 minus 2 plus c plus d equals to 1. Okay, and then easily we can do it. D is 4 and c is negative 3. This is the final answer. Beautiful. Beautiful. That's we can see we can anti-differentiate twice, or if we need, even more. Anti-derivative. Okay. And now let's maybe look at one more question and we will be done. You can still practice, you can still look at these notes and solve all of the problems that I placed here, check against my solutions, and yeah, then you will be confident with your anti-differentiation. Okay. Yeah, now we can see, find the general indefinite integral. I'm just looking, I'm just using the integral notation, the same thing. In order to integrate, we will just find the antiderivative. That's when we can copy 10, x to the power of 4, antiderivative is x to the power of 5 over 5. Excuse me, copy constant. Integral or antiderivative of sine of x is actually negative cosine, because derivative of negative cosine is positive sine. Am I right? Yes. Okay. So this one will be 2x to the power of 5 plus 2 cosine of x plus the constant. We do not have an initial condition, then constant will stay. And so we can see we did anti-differentiate. Yeah, that's mean if we see the general form or if we see the indefinite integral form, we will anti-differentiate. Okay. Oh, I have another one. This one is, but we have one more question. But yeah, let's actually, yeah. This one is interesting because cosine of x over sine square of x, I don't think this was in our table of formulas, yeah, because we had a couple of tables. But what we can do, we can definitely try to rewrite this. Always when you see the trigonometrics, sine of x, sine of x. Trigonometrics, we always try to, yeah, rewrite, simplify. 1 over sine is cosecant of x. Cosine over sine is cotangent. And now we know the antiderivative for cosecant cotangent is actually negative cosecant of x plus the constant. And why is like this? Because derivative cosecant, yes, because derivative of this is antiderivative, is basically cosecant of x, cotangent of x. Oh, no, not constancy. Yeah, that negative we can see it's compromising. It's not, now it's positive. That's we good. But remember to rewrite. Yeah? And especially when we see quotient or product, we have to do it. This one we know. This one is the direct antiderivative. Okay, let's do one more problem now, and then we will be done. Oh, I type this. This one you can do it. This one you can do it. Okay, that's me now. Yeah, let's look at some, because we know we can when we have position function, some application of the velocity, acceleration, when we have position function, in order to find the velocity, we will differentiate. In order to find acceleration, we will differentiate again. Now, backwards. Having the acceleration, we have to recover velocity, then we will anti-differentiate. Having a velocity, we have to recover a position function, we will anti-differentiate. Yeah? Okay, so that's what we will do. Let's look at maybe one question. This one you can try. This one actually you can try to do without looking at the solution. Okay, try to pause the video, try to solve it, and then check. This one is not solved, but we will solve this one. Okay, because this one is a nice exam type question. Let's finalize the session with this. A particle moves in a straight line and has a velocity v at t, 3 sine of t minus 10 cosine of t. An initial position s at 0 equals to 1. Find a position of a particle at the time t equals to pi. Okay, so we have the velocity. In order to recover a function, we will integrate the velocity with respect to t. Integration, of course, means anti-differentiation. Okay, that means we will integrate 3 sine of t minus 10 cosine of t. That's just the basic. Okay, copy 3. Integral or antiderivative of sine is negative cosine of t. Copy 10. Integral or antiderivative of cosine is just sine of t plus the constant. That means this is s of t. Let's write this nicely. Negative 3 cosine of t minus 10 sine of t. Let me just double check. Cosine is sine and sine is negative cosine. Yes, the negative. Yeah. Okay, now we know that s at 0 equals to 1. Then let's replace t with 0. Negative 3 cosine at 0 minus 10 sine at 0 plus the constant equals to 1. And now cosine at 0 is 1. Sine at 0 is 0. That means constant c equals to, okay, let me just write negative 3 minus 0. That means constant c equals to 4. Yes, we will be adding 3 to both sides. Okay, that means the position function now equals to negative, yeah, because this was the most general antiderivative. Now we know the constant, negative 3 cosine of t minus 10 sine of t plus 4. 4 constant. And just the position at pi. Unit circle. Again, negative 3 cosine at pi, negative 10 sine at pi plus 4. Negative 3 cosine at pi is negative 1. Sine at pi is 0. I hope everything is correct. Positive 3, positive 4, 7. 7 is the position. Whatever are the units, maybe meters, maybe it's a particle. That means maybe millimeters. Okay, 7 is the correct answer. Right? That's how we can anti-differentiate, just flipping, reversing, undoing derivatives. Thank you, and please enjoy every single question that is placed in this lecture notes. Thank you.